record. Okay, so we're going to continue with 2.8. So the last thing we talked about was, least upper bound and greatest lower bound, right? Properties, right? And
Yes.
so here we have, using axiom D, we can easily prove the following. So each non-empty set bounded from above has the least upper bound. Right? So, and looking at axiom D, rounding non-empty set bound from below, greatest lower bound. So their equivalent is obviously, where we're going with that, right? To see a D implies D prime and conversely D prime implies D, it's suffice to consider the set of negative elements of the set. So if you look at, if you look at a set, let's talk about this really quickly. So this is the proof, right? So which way are we going? We're going to say D implies D prime, all right? So let me read D, okay? And I'll tell you how it implies D prime, and I'm not going to write anything up. It's going to be quick. Is that okay?
Okay.
Let's look at D. For every, and let me get rid of this stuff. How about let's get rid of all this stuff. Oh, wow, that wasn't, let me, one sec, let me get rid of all this stuff. Okay, I can't get rid of all the stuff. It's just the little stuffs, but that's enough little stuffs. All right. For every non-empty set bounded from below, all right, so you have a set bounded from below, there exists a greatest lower bound. So that is an axiom. Is that okay? So we're assuming this to be true. Is that all right? Now we want to assume this and somehow prove D prime. Right?
D prime was
for every non-empty set bounded from above, there exists a least upper bound.
okay.
If you take all the elements of your set and you take the negative of them, the set bounded from below becomes, where's D prime? Bounded from above. The negative makes it,
right,
and this greatest lower bound turns into a least upper bound, and vice versa. And so looking at the negatives of the elements, D implies D prime, and likewise D prime implies D. You can go either way. Is that all right? So that's what this is. That's what this is. I mean, I didn't read it word for word, but that's logically what he does. Any questions or comments? I can go in like a little more detail, but I think that's sufficient.
right.
I don't want to do any more on that one. It's not too interesting, in my honest opinion. So good. So you could take your pick of D or D prime, depending on your set and what you're examining and what you're working in. You know what I mean? No big deal. And good. Okay. In order to avoid possible misunderstanding, it should be strongly emphasized that if we say the set P has greatest lower bound M or least upper bound M, then M need not belong to P. Okay, that's a big deal. Is that okay? All right.
Okay. So
you can have a greatest lower bound, but that it doesn't have to be in the set, right? Only means that a number with the required properties exists. That's all it means. Right?
Right.
And for example, if you take a look at all rational numbers less than the square root of 2, that's a set.
Yeah.
I'm talking about the least upper bound. I'm not talking about greatest lower bound. You just make it a negative, but no big deal. So I'm talking about the least upper bound. And so least upper bound would be the square root of 2.
But it's not, yeah, but it's not in the set.
It's not a rational number. So okay.
Sorry, my brother's here.
No, we're good. We're good. That's good. Take your time if you need. I just took like way too much time. So for each pair of real numbers, A and B, only one of the following relations holds. A is less than or equal to B, or B is less than A. Yeah, this is a consequence of 2.6.4, which I don't want to even go back, but we have this trichotomy, and this is 2 of the 3, and this is the third. So it's, you know what I mean? It's either one or the other kind of gig, you know what I mean?
Yeah.
Then, I don't really want to get into that. If A is less than or equal to B and B is less than or equal to A, then A is equal to B. Okay, well, this inequality implies either this holds or this holds. Boom. Is that good?
Mhm.
And this inequality implies either this holds or this holds. Okay. Yeah. But this trichotomy thing tells us we cannot have A is less than B and B is less than A happening at the same time.
Right.
So that's it. A must be equal to B. No big deal. By this trichotomy. I think that's what 2.6.4 is. I'm not going back into it, but it really it is. Because one of these holds, it's 1, 2, or 3, and these two cannot simultaneously hold. So this must hold, right? So I think 2.6.4 is trichotomy. I'm not going back and looking. All right. Any questions on that?
It's pretty good so far.
All right. Did you take a look at the exercises, the exercise set here?
I've not.
Okay. Well, it's funny because I think all these ridiculous math people, we do all the same nonsense. Look at number 3. I swear to you, I did not look at this before today.
Find the least upper bound of the set of all rational numbers. Hey, wait, you just said, wait.
Yeah, I just said that, right?
Yeah.
It's funny because we all think the same, it turns out, and that's a good set. It's a good set. So what is it? What's the answer?
2.
No.
Wait, oh, rational. Wait, find the least upper bound of the set of rational numbers whose square is less than 2. Oh, so what is that like? It's
Square
just
root of 2. Square root of
yeah,
2.
it's square root of 2 because
That's it. That's it. That satisfies, right? That's the least upper bound of the set of all rational numbers whose square is less than 2. Boom, 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 boom. We're done. Cool. Cool. So it works. So how about, let me actually take a step back. Do you have any questions from the previous problem set? Because I don't recall if we talked about those at all. Should we look at those before we continue? Yes or no?
wait, did we not talk about them?
I don't remember. I mean, it's like a week. I don't know. I think we did that. Okay, yeah, we did that because it was 0. That was the funny thing. The set 0 satisfies all the conditions. So we have to kind of eliminate that if we're going to actually talk about something interesting, right? We have to get rid of this trivial case. Yeah. So I think we did most of those. Okay, enough said. All right. Do you want to talk about any of these problems or do we continue into 2.8? Your call, sir.
Talk about problems.
Okay, so provide the details of proof. I don't want to do that because I think I outlined it and it's really straightforward. So I don't really want to do that. Let's take a look at number 2. Find the greatest lower bounds and least upper bound of the following. Okay, so what is the greatest lower bound and the least upper bound? Let's talk about A.
So the least upper bound is just 1
Okay,
for A.
1 is an upper bound and anything less than 1 would not be an upper bound for A. So yeah, 1 would be the least upper bound. Not too interesting. Not too interesting.
Yeah. And then the greatest lower bound is probably 0.
Yeah, 0 would work because 0 is a lower bound. It just is. And anything bigger than 0 would actually not be a lower bound. But that's an interesting statement, right? That's not like the 1. The 1's not as interesting. So I like that one better. Okay, so that takes care of A. Is that okay?
Yeah.
All right, let's take a look at B. Help me out. You pick greatest lower bound or least upper bound? I guess greatest lower bound is the first one we talked about. So because I read that first.
So like, okay, so the graph of this is like an oscillation, but like it gets closer and closer to 0.
Yeah, I don't know about the graph, but yeah, you can see
Or-
the graph. You don't need a graph, right? You're just talking about, what's going on here. And
So with the greatest
you're
lower,
saying it's getting closer and closer to zero. Let's take a look at these negatives. What's going on here?
oh wait, no, it gets, no, sorry, it's getting farther and farther away from zero. My bad.
Well, I think the statement is -1, right?
Yeah,
-1
it's
is
getting
positive.
farther away from zero.
Yeah,
So would one and -1 be the greatest and least,
yeah, I
greatest?
think it's the other way around, though. I think it's, -1.
Yeah, sorry, the greatest lower
Fine.
bound is
We're good.
-1.
I completely concur. This
Yeah.
was already done. That gets an X because we did that during class, right? We didn't, um, show that, okay, so consider this where AN is defined inductively. Are you familiar with this kind of a thing? Yes or no?
It's just like, I mean, it's self-explanatory, right? You just, to get the next term, you get the term before it and do something to it.
Yeah. I mean, that's how you get this, right? Let me take
Yeah,
a look.
in this case, you do 3 times that term plus 4 divided by 2 times the term plus 3, and that gets the next term.
Yeah, so
Um,
okay. So let's get the first couple terms. Let's see what this thing looks like. So we start with the number 1. That's the first term. What's the next term? So it's 7 over
7, 5?
7/5. Thank you. So
Yeah.
now it's gonna get nasty. Can you give me the next term, please?
Uh,
No, I'm gonna
10.
let you do it because I don't even have anything to write with, and this is dirty, right? This is what we call dirty.
Yeah. Hold on, let me get something really quick. There we go. Just gonna write it down, calculate it really quick. Hold on. Yeah, this is not ideal. 41 over 29s. That's what I got.
Okay, what's 41 over 29? Do you have a calculator?
I should, hold on. Uh, 41 over 29. Like in decimal form, or
Yeah.
it's like what, how many digits do you want? Like how many?
I want you to tell me it's around 1.5, which I know it
Like,
is.
yeah, it's around like 1.41.
Okay,
For-
sounds good. So, good. Okay, so what you're telling me is there's something going on with this, 1.5, right? Right,
Yeah.
so, good. I don't think we have time to continue, right? I mean, plugging in, without any software and stuff. So what can we say, right? Can we find a bound for this term when we, assuming we start with the number 1, right? Assuming we're starting with 1, because if you start with 10 million, maybe it's a little bit different, right?
Yeah, so what we can say is that, um, because like the way you get the next term, the numerator is always going to be greater than the denominator, and it's positive, right? So we know there's there's a greatest lower bound, and that's 1.
Okay, so what you're saying, okay, just 1 second.
That's what we can say right off the bat.
So what you're arguing right now is that it's bounded from below, right? Good. Okay, so we're set. So we're done, right? Good. Thank you. So you're halfway done.
Yeah.
How about from above?
Hmm. Um,
Let me show you a little trick too. Okay. When you have something that's
You're gonna
recursive,
have to consider like the rate at which it's increasing.
yeah, let me tell you, let me show you a little trick. So assuming it has a limit. So this is just cheating what I'm doing right now, right? Assuming it has a limit. This is actually cool. So the limit would be L. Is that okay? As n gets large enough, it's gonna be really close to L. Is that fair?
Sure, yeah.
This would be 3L plus 4. 2L. That's an ugly 2L plus 3. Can you solve this for L?
Yeah, but so why are we wait,
What was that?
um
Oh, this is cool.
so L is just what is L again? That's just a really huge well, that's
limit,
just like
the limit, if the limit exists for this,
Mhm.
it's going to be the square root of 2.
Huh.
Yeah, the limit to this can only be the square root of 2. So I'm assuming the limit exists. I did not prove the limit exists. So what I just did was called cheating. All right, that's cheating. How do I know the limit is there? I don't. You have to show the limit exists, right?
Right.
But assuming it exists, it's a square root of 2. Cool little trick. Cool little trick. So, and I think this thing is monotone, right?
I think so too.
So that means,
Looks like I don't know what to work with because of I have learned this before, like you can use different tests, but it's like we're only given a few axioms in the book. I'm not sure how to only use those and do it.
yeah, no, yeah, no, I think it seems to me that square root of 2 is definitely going to be a bound for this, if this thing's monotone. And let me leave this out as a question for you at this point. Find, a bound from above, maybe just saying 2, proving an is bounded by 2 for all n. I think square root of 2 is perfect. Okay.
Oh wait, oh, so okay, yeah, we're not trying to find the least upper bound. We can just plug in the bound.
Yeah, we're looking
Yeah.
for, yeah.
Yeah,
Actually, I
that's
found the least upper bound. Okay, Rumi, let's get this straight. I actually gave you the least upper bound. It's a square root of 2.
square root of 2. Yeah.
Okay, okay, stop that. We already did that. So the question is, can you find a bound, right? Because if you have an infinite sequence that's bounded above, it has a limit, okay? I mean, if it's bounded above and below, that you don't know that, but that's a standard analysis result. So you already gave me the below bound, and it's an infinite sequence. So can you find me a bound from above? And that's it, right? That's it. So, yeah, you could, I don't care what it is. You could use 10 million as a bound. I think you can get that pretty easily. Okay. But it's cool. Can you find the least upper bound? Yeah, actually we got it. Because if there, was a limit, it would be the square root of 2. And you're never going to have the square root of 2 because these are all rational numbers, right? So, yeah. But in order to show it's a least upper bound, you're going to have to show it's monotone, monotonically increasing, because just because, because it could oscillate, right? It could oscillate and have that limit, and that would be a problem logically, right? So if you want to show it's a least upper bound, you have to actually prove it's monotone as well. So I'm gonna take a pass on those. We have the least upper bound, but we're not gonna go through that. All right, so that's, I guess, for next time. Connection between real and natural numbers, assuming there exists a set R with operations plus dot, inequality less than, satisfies axioms script R, which is the 10 axioms we talked about, I guess, last time, right? And so we can select, and so assuming there's a set R that satisfies all these axioms, so R satisfies R. That's the statement, right? Script R is the axioms, R is the set that satisfies the axioms. Is that okay?
Uh, let's
Okay.
see.
This is a set, and this is a set of axioms. The set that satisfies the axioms is R. The axioms is script R.
Okay.
Is that okay?
Yeah.
All right, so we have a script R and an R. They're connected, but they're not the same, right?
Yeah.
All right, so we can select from the set R a non-empty subset N satisfying axioms 1 through 4. Boom, 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 right? Is that okay?
So like the subset N, yeah, subset N will still inherit all the axioms. Well, at least axioms 1 through what is that? What is IV? Like 6 or 5?
Axioms 1 through 4. What do you
That's
like?
4? Oh, okay.
Yeah, Roman numeral 4. Yeah. You're worried about coronavirus, the IV stuff. No, we're talking about 4.
Yeah, I know. I don't know Roman numerals. I need to learn them.
No, they're really hard. It's very complicated. Next time we're gonna spend all day on Roman numerals. I'm joking, right? I'm just kidding around. I'll spend like all next week. We're gonna do Roman numerals. I'm kidding.
So what is 5? Like V? 5 is V, right?
5. What's 5? What are you talking about?
A Roman numeral.
It's a V. Yeah, it's a V.
Okay.
Yeah, I think an L is 50. X is 10. I think an L is 50. I think. And whatever. I think. I'm not sure. Only because of Super Bowls, All right, so this is outlining connection. So, real numbers come from these axioms. And then, we have a subset that satisfies only axioms 1 through 4. And those are your natural numbers, right? So, okay. So let me close the door because it's getting kind of wild. So drum roll. All right, yeah, we're kind of, I think this might be a good place to just stop.
Okay, yeah.
Because there's a lot of words, you know what I mean? It's like, I have to do some reading here, man. Yeah, this is probably a good place, timing. Sorry it took so long.
Yeah.